Hello everyone and welcome to our final project presentation. I am Brajesh representing our team and today we are excited to present our work on Adaptive Octopus Inspired Optimization or OIO for short. In this project, we ventured into the fascinating world of bio-inspired computing. Nature has always been the best engineer and we took inspiration from one of the most intelligent creatures in the ocean, the octopus. We selected the octopus-inspired optimization algorithm, a relatively new and powerful meta-heuristic as our base. But we didn't just want to reproduce existing work, we wanted to understand it, break it, and then build it back later. Our primary goal was to address a fundamental limitation we discovered in the original algorithm, its inability to adapt to different problem landscapes. It was like a car stuck in one gear. By introducing a novel diversity guided mechanism, we have created a version that is smarter, more robust, and capable of solving complex mathematical problems more efficiently. Over the next 20 minutes, my team and I will take you through our journey from theoretical foundation to our novel implementation and the final statistical results. To understand why our work matters, we first need to define the problem we are solving. Imagine you are dropped into a massive pitch black mountain range. Your goal is to find absolute lowest valley in the entire world, what we call the global minimum. The challenge is that you cannot see the map. You are optimizing in the dark. You can only look at your feet to see your current altitude. In computer science, we call this a fitness landscape. Now, why is this hard? Many traditional algorithms like gradient descent are like hikers who only walk downhill. They might walk down into a small valley and think, I found it, I am at the bottom. But in reality, there is a much deeper canyon just a few miles away. This is called getting stuck in local optimum. This isn't just a theoretical game. This problem exists everywhere. Training neural networks, finding the best weights, drug discovery, folding proteins into the lowest energy state, logistic, finding the most efficient delivery routes. We need algorithms that are smart enough to escape these fake valleys and find the true solution, matter how rugged the terrain is. So, how do we solve this? We look to nature, specifically the octopus. The octopus is unique in the animal kingdom because it is decentralized nervous system. Its brain, the head, makes high level decision, but its arm, the tentacles, have their own mini brains and can explore independently. The OIO algorithm mimics this exact structure to solve optimization problems. The head represents the best solution found so far by the entire swarm. It acts as a coordinator, the tentacles. These are independent search agents. They move around the search space looking for food, which is our case means better solutions. The algorithm combines two powerful mathematical strategies. First, Levy flights. This represents the tentacles reaching out blindly. It allows for long, random jumps to entirely new areas of the map. This is called exploration. Second, PSO like movement. This represents the tentacle digging in. It moves towards the best known spot. This is called exploitation. By combining these two, the octopus can search wide to find the valley and then dig deep into the to find the bottom. Our project was structured among around three clear scientific objectives. First, reproducibility. In science, if you can't reproduce it, it doesn't exist. We spent the first phase of our project simply verifying the claims of the original OIO paper. We had to ensure the code actually works and produce the results it claims. Second, novelty. We didn't want to just copy, we wanted to innovate. We identified a critical flaw in the original design. It uses static fixed parameters. It decides when to explore based on a fixed schedule, not based on whether it's actually stuck. We proposed adaptive OIO to fix this, making the algorithm self aware. Third, validation. We rigorously tested our new algorithm against the original using the CEC 2022 benchmark suite, which is the gold standard in the field. My personal contribution to this project was leading this theoretical research. I defined the problem scope, analyzed the biological inspiration, and identified the static parameter limitation that form the basis of our entire novelty. Now I will hand it over to Daksh, who will walk you through the code bases and the challenges we faced in reproducing this complex algorithm.
Okay. Hi, my name is Daksh Arora and I will take you under the hood of our project. When we first actually downloaded the official repository for OIO, we were met with a bit of a chaotic structure. It was designed for specific researchers' machine, but not for public use. To make this project manageable and professional, my first task was to reorganize the entire code base into a clean and modular structure. So, this is the repository of our project. Let's look at the actual project files. So, this CEC folder has all the files which were initially there. Uh, CEC stands for Continuous Evolutionary Computation. This folder contains the original implementation of OIO algorithm and the complex CEC 2022 benchmark functions. We kept this separate to preserve the original logic. Okay, next week, all of our actual innovation that we did is present in this new setup, which has our adaptive OIO function feature that we had over the original OIO repository. Uh, so basically, the core logic of this OIO is defined in this file. I'll show you the class of octopus. So this is the champion octopus class, and we have the tentacles class. So this is a champion tentacle class defined here. So this all file is the basically the blueprint. It defines the octopus and tentacle class. It manages the entire life cycle of the swarm from initialization and till the final result. Understanding this file was basically the key to everything. Okay. Now, simply organizing files was not really enough. Reproducing academic code is rarely straightforward, and we hit several roadblocks immediately. We call okay, so let's go through the challenges. So, the first challenge that we faced was the missing library challenge. That there were libraries like OPF, UNU, and Matplotlib, whose basically the code relied on specific and undocumented versions of these libraries. The code simply wouldn't run basically. And I had to reverse engineer the requirements by analyzing the import errors one by one to rebuild a working environment. Next was the problem of hard coded file paths. So the original code had absolute file paths, which the researchers desktop can only understand. So this meant the code would crash on anyone else's computer. So I refactored this to use relative paths, making our project portable. Next was the problem of language barriers. A significant portion of the code, comments, and more importantly, the output logs were in Chinese. This made debugging extremely difficult for our team. I went through the code and translated these logs into English so we could actually understand the algorithm, basically, what the algorithm was doing in real time. My individual contribution was solving three reproducibility issues. I refactored the code base, translated the logs, and created the verification tools to ensure we had a solid foundation. Right. Okay. Now let me help you in verifying this quick test files. This quick test file is basically for us to run the actual OIO algorithm. So to prove that we successfully made this code working, I created this script quick test. So you can see here that it imports the actual algorithm, which is this. Let me help you go through it. So this is the algo name. This is OIO algorithm inside this. So we can see that this is basically over the OIO, a wrapper over the OIO. Okay. Okay. You can see here this basically is importing the champion OIO algorithm, and we can also run a quick test for seeing how it actually works. Let's run a really short test with max evaluations only 1000. So we are expecting it to give us not so really good results. So let's try running this. And when we run it, we see that the best fitness is around 14,000, which is not really that good. We want the fitness to be as less as possible, because it kind of denotes the height, the least height that we are able to reach. So if it is 14,000, it is not really good enough. Let me run it for, let's say, 20,000. So we are expecting a better result here. It will take bit of a more time, but in this case we can see that our fitness is coming as 1300, which is very, we can say that this is a really good result. So this is our code file of quicktest.py, which helps us to run the actual algorithm. And running this script was the basically the first time we saw our algorithm can, not our, but OIO algorithm can actually work on our machines as well. So now let's go to the how the OIO works. Now that we had the code running, we could analyze how it works, and more importantly, why it was not good enough. The original OIO uses a probabilistic approach to decide between exploration and exploitation. So let me show you the original code. Here, let me show you how we decide on things. So this is basically the optimize function, optimize method in the champion tentacles class. This loop is basically the heartbeat of the algorithm. In every iteration, for every tentacle, it has to make a choice, right? So we make this Levy mask, right? Look at this line. It compares a random number against Levy probability. If the number is lesser, it creates a mask for Levy flight. This is a long random jump. This is basically exploration. And if it is not less but greater than the random number, then we will do a PSO update. This is like moving towards the best solution known till now. This is known as exploitation. So we are dividing our exploration and exploitation based on this random number which is being generated here. Okay. Crucially, look at how Levy probability is defined. So this is being calculated on based of progress, uh, which is basically time. This algorithm doesn't really know if it is stuck in a valley. The algorithm doesn't know if it has already found the solution. It just blindly follows the time-based schedule. This blindness is the critical flaw that we identified. It led to wasted time exploring when it should be digging, or digging when it is stuck. So, this analysis set the stage for our innovation. Now, I'll hand it over to Harshit, who will explain how we fix this in our adaptive logic.
Thank you, Daksh. I am Harshit and I will be presenting the core innovation of our project. As Daksh just demonstrated, the original OIO algorithm suffers from a critical weakness, that is, it is blind to its own progress. It follows a predetermined schedule like a train that leaves at 9 am regardless of whether there are passengers or not. For example, the inertia weight W simply decreases linearly from 0.9 to 0.4 over time. It assumes that at the beginning you always want to explore and at the end you always want to exploit, but real world optimization problems are not that simple. Uh, Suppose scenario 1, what if the algorithm gets stuck in a deep trap early on? The schedule says keep exploiting, which just digs the hole deeper. Where, on the other hand, consider the scenario B. What if it finds the solution immediately? The schedule says keep exploring, which wastes valuable computational time. We realize that a truly intelligent agent should not just follow a clock; it should react to the terrain it is traversing. So, to solve this, we introduced adaptive octopus inspired optimization. We call it AOIO. My contribution was designing and implementing this novel adaptive logic. Okay. The core concept I introduced is diversity guided adoption. So, what is diversity? For that, imagine our swarm of tentacles. If the tentacles are far apart, scattered across the map, the diversity is high. This means we are exploring well. If the tentacles are clumped together in one spot, the diversity is low. This usually means they have all converged. Okay. So for this, we created a feedback loop based on this metric. Okay. So there will be two things. One is calculate the diversity. So in each single iteration, we compute the standard deviation of the swarm's position. And the second thing that we do is check the state. So if diversity is too low, we will do something. If diversity is high, we will do something. So if diversity is too low, we kept less than 0.1, we are likely stuck in a local optimum. We call this stagnation. The algorithm automatically triggers an emergency eject. It boosts the Levi flight probability to force the tentacles to fly apart. And if the diversity is high, that is, if it is greater than 0.5, we are scattered. We call this convergence mode. The algorithm increases the social learning factor to pull the tentacles together towards the best spot. So these are the two cases based on the diversity value. Okay, so this makes the algorithm self-aware. Okay. Now let's walk through the implementation. So because the talk is cheap, so let's go to the implementation part. Okay, so to implement this, we created this new file adaptive.oio.py. Okay, so first I added this helper function calculate diversity. Okay, so it takes current position of the swarms as input and computes the standard deviation across all dimensions. It then averages them to give us a single number, and that we call it a diversity score, and that represents how spread out the swarm is. So based on this diversity score, we will make the cases, and so based on the diversity score, now we will implement our optimize function. So what happens in optimize function is, so let's look at the main logic of this optimize function that lies in this loop. So this is the optimization loop, and this is where the magic happens. Okay, so this block, so if we say if diversity score is less than 0.1, we call this block stagnation detector. So if the diversity ratio drops below 10%, we assume we are stuck. See what happens here. I force W equal to 0.9. This is high inertia. It makes the particle hard to stop. I force Levi probability equal to 0.6, and this cause high chaos. I am essentially shaking the box to force the algorithm to break out of the trap and explore different paths also. Okay. Okay, so this was for the diversity ratio less than 10%, and if it is greater than 0.5, we have some other cases. And what we do here is we call, first of all, we call this convergence detector, and if diversity is high, we set C2 equal to 2.5. And what is C2? C2 is social learning factor. So I'm telling the tentacles that stop wandering around, trust the leader, and come to the best spot found. All right. So these were the two main functions that were different from the standard OIO algorithm. And this simple logic allows the algorithm to breathe, expanding when it's stuck and contracting when it's successful, and not just following the simple clock. It adapts dynamically to whatever landscape it finds itself in without us having to manually tune parameters. Right. So now I will hand it over to Dipesh, who will show you the statistical proof that this actually works. Thank you.
Thank you, Harshit. I'm Dipesh, and I will be presenting the results of our work. A novel idea, no matter how clever, is only as good as its results. To validate our adaptive OIO, we didn't just run a few random tests, we followed a rigorous scientific protocol. We utilized the CEC 2022 suit benchmark. For those unaware, CEC stands for the Congress on Evolutionary Competition. Their benchmark suite is the industry standard for testing optimization algorithms. It contains extremely difficult mathematical functions designed to trick and trap optimizers. We selected two representative functions for our duel. Function f1, which is unimodal. This is a simple value. It tests pure speed and convergence. Function f2, multimodal. This is a landscape full of traps and fake values. It tests robustness. To ensure a fair fight, we gave both the original OIO and our adaptive OIO the exact same budget, 20,000 function evaluations. This ensures that any improvement we see is due to intelligence, not just doing more work. My contribution was designing this experimental protocol, writing the comparison scripts, and performing the statistical analysis of our result. Now, let me show you the test bench I built. I wrote this script, run comparison.py, to automate the race between the two algorithms. Here you can see the main function. It iterates through the function f1 and f2. Inside it initializes both the original OIO and our adaptive OIO. Here, we enforce the strict budget of 20,000 evaluations. I also added plot convergence function to automatically generate convergence plots so we can visualize exactly when one algorithm overtakes the other. This script is designed to be one-click reproducible. Anyone can download our code, run this file and get the same exact results. So now let's see it in the action. I am going to run the code and let's see the results. So I am running the script. The script is now initializing the CEC 2022 functions. It is running the original OIO on F1 and now it is running on adaptive OIO on F1 and moving to F2 and done. So let's look at the output right here in the terminal. Look at the mean fitness column. Remember, in the optimization, lower is the better. 0 is perfect. On F1, original OIU got around 3200. Our adaptive OIU got around 1900. That is a massive difference. So let's analyze those numbers. On function F1, our adaptive OIU achieved a 40% improvement in F1 convergence accuracy. Because the landscape was simple, our convergence detector kicked in, switched to exploitation model and zoomed straight to the bottom. The original algorithm wasted time exploring unnecessarily. On function F2, the trap function, we also outperformed the baseline 450 versus 500. This proves that stagnation detector worked. When the tentacles got stuck in the local traps, the diversity dropped and the algorithm successfully forced them to jump out. Finally, we can check the cost. Did we make the code slow? We measured the wall clock time. Original OIO has 0.34 seconds per run, while adaptive OIO has 0.35 seconds per run. The difference is only 0.01 seconds and it is negligible. This confirms that our diversion calculation is computationally cheap. We added significant intelligence without adding any noticeable overhead. So, coming to the conclusion, to summarize our project, we successfully reproduced the complex OIO algorithm from scratch. We innovated by introducing a diversity guided adaptive mechanism. We proved that our new method is statistically superior, achieving 40% better convergence while maintaining the same hardware efficiency. We believe this adaptive approach is the future of bio-inspired optimization. It turns a blind search process into a self-aware and intelligent agent. Thank you for your time.